We have so far completed the introductions of fire and explosions and their definitions. The second part of this lecture series is talking about the calculations of the flammability characteristics of liquids and vapor. These figures is a plot of concentrations versus temperatures and show how several of these definitions are related. The exponential curve in this figure represents the saturation's vapor pressure curve for the liquid material. Typically, the UFL stands for upper flammability limits increases and the LFL lower flammability limits decreases with temperature. The LFL theoretically intersect with the saturation's vapor pressure curve at the flash point, although experimental data do not always agree with this. The octo-ignition temperature is actually the lowest temperature of an octo-ignite regions. The behavior of the octo-ignition regions and the flammability limits at higher temperatures are not known. The flash point and the flammability limits are not fundamental properties but are defined only by the specific experimental apparatus and procedures used that is shown in the next slides. The flash point temperature is one of the major quantities used to characterize the fire and explosion hazards of liquid. Flash point temperatures are determined using an open cup apparatus shown in this figure here. The liquid to be tested is placed in a cup here, and the liquid temperature is measured with a thermometer, while a Bunsen burner is used to heat up the flame, is used to heat up the liquid. And if you can see, there's a small wand that has an open flame that is being established. And during the heating, this wand is slowly moved back and forth over the open liquid pool. So eventually, a temperature is reached where the liquid is volatile enough to produce a flammable vapor. You may see a momentary flashing flame. The temperature as the first occur of this flame is what we call the flash point temperature. Please note that the flash point temperature is only the momentary flames. At higher temperatures, what we call the fire point temperature is required to produce a continuous flame. The flammability limits for vapors are determined experimentally in a specifically designed closed vessel apparatus, as shown in this figure. Vapor-air mixtures of known concentrations are added and then ignite. The maximum explosion pressure is measured. This test is repeated with different concentrations to establish the range of flammability of the specific gases. Very often, the LFL and UFL for mixtures are needed, as in nature we often have the presence of different types of vapor mixture in the air. So these mixtures limits are computed or are calculated using the equations shown in these slides, where LFL stand for lower flammability limit and UFL stand for upper flammability limit. In these equations, there are certain assumptions that is inherent. First, the product heat capacities are constant. Second, the number of moles of gases are constant. The combustion kinetic of the pure species is independent and unchanged by the presence of other combustible species. And the adiabatic temperature rise at the flammability limits is same for all species. So if we want to use these formulas are only applied with the same temperatures and pressure. In general, the flammability range increases with temperatures. So if there's a different temperature used beyond the room temperatures and we want to estimate the lower flammability limits and the upper flammability limits, we can use these two equations that is shown here. However, pressures has very little effects on the LFL except as very, very, very low pressure, where flames do not propagate at all. Therefore, if there's any pressure change, the only things that will get affected is the UFL. So these formulas can be used to estimate the upper flammability limits at a different pressures. Do note that this pressure is the absolute pressure. There are some situations when the experimental data are not available, then we can actually use the stoichiometries to calculate the concentrations of fuels as per written in these equations here, in the chemical reactions equations, and to calculate the Z value. So with that, the stoichiometric concentrations of most organic compound is using by this general combustion equation. It follows the stoichiometry, and the additional stoichiometries can be shown, and once we put in the data, this is how you can estimate the flammability limits without the experimental data, just by using its pure stoichiometry equation. So first of all, this is the first example that we have for today's on the fire and explosion. So the question is, what are the LFL and UFL of a gas mixture composed of 0.8% of hexane, 0.2% of methane, and 0.5% of ethane by volume? So now first, of course, we are going to put up some table here. So we know we have volume percentage here. Okay, and so we want to know what is our mole combustible. Okay, or mole fractions for combustible. And we also want to know what is our LFLI and UFLI for each of these elements here. So we have hexane, we have methane, and we have ethylene. Okay, so the gas mixture here is 0.8%, 2.0%, and 0.5%. In other words, the total combustible here is, okay, this is 3.3%, and we have to extend it a little bit. And the rest will be air. So air, you get 100% minus 3.3, that's you get 96.7 volume percent. So in order for us to calculate what is the mole fractions of the combustible here, so what we have is 0.8 divided by 3.3, because this is your total combustible. You get something like, let me calculate. This is 0.8 divided by 3.3. You get 0.24. Okay, same thing that you do 2.0 divided by 3.3, you get something like 0.61. And the last one, you get like something along 0.15. So total, you add up, it will be 1.0 here. Okay, so how do we find the LFL and UFL data? So this is where we refer back to our handbook. Okay, so scroll all the way down. Okay, so to this table, AB1, where you can see there's a LFL and UFL data here. Okay, so I'm going to highlight a bit, and later on I'm going to delete it once I'm done. So what I need here, hexane. So can I find hexane? Yes, hexane is here. Oops. So how come I cannot draw the data? Hexane, and so The LFL is 1.2 and the UFL is 7.5. Then I also need methane over here, 5.0 and 15. And ethylene, yes, is here, which give us 2.7 and 36. So this is where you put the data back to where we have. So hexanes 1.2 and 7.5. We have 1.2 here, 7.5 here, and methane we have 5 and 15. We have 5 and 15. And the last one we have ethylene 2.7 and 36. 2.7 and 30, sorry, 36.0. So for us to calculate the LFL mix, the formulas to be used is your total concentration divided by your total concentrations over LFLI. In this case, because the concentrations here is at 1.0, yeah, this is the value. So what we have here is 0.24 divided by 1.2 plus 0.61 divided by 5.0 plus 0.15 divided by 2.7, and you will get your data. Same thing with the UFL, upper flammability limits mixture. You do the same, so it will be over, because I'm running out of space to write. Okay, YI over UFLI. And again, you have 1 over 0.24 divided by 7.5 plus 0.61 divided by 15 plus 0.15 divided by 36, and you get your UFL mix. So that you resolve these questions, number 1. So now we come to our second example to estimate the LFL and the UFL for hexane and compare the calculated limit to the actual value determined experimentally. So just now we have from questions 1, we already find what is our LFL and UFL for hexanes over here. So this is the value. So let me drop it down from experiment. So this is 1.2 volume percent, and this is given as 7.5 volume percent, okay, from the experiment. So now in these questions, we're going to calculate using the stoichiometry. So first of all, we write down the stoichiometry of hexane. C6H12 plus 2, 14 plus unsure amount of oxygens. Normally we put in Z here, equals to MCO2 plus X over 2H2O. So if we are to fill in the blank here, this we will have 6 CO2 here, and now amounts of hydrogen. So X here, this whole value will be 7. Therefore, your X will be 14, and Z will be 6 plus 3.5. Oh, yeah. And we get 9.5 here. So we have our M equals 6, X equals 14, Y 0. We don't have any values for y. Okay, so now we can calculate our LFL. Given with the formulas, which is 0.55 divided by 4.76 m plus, what was my earlier formula? 1.19x minus 2.38 y plus 1. Same thing with UFL. We have 3.50 times 100 divided by 4.76 m plus 1.19x minus 2.38 y plus 1. So now we can calculate, just put in the value in there. Then you can calculate your LFL. Just do one with a quick example. So here we have 55, 4.76, and m is 6, plus 1.19, 14, plus 1 because y is 0. Okay, and if you calculate, so with this, if you take out the calculator to calculate, you will get something like, let's see, 1.19 volume percentage. So if we are to compare the earlier data, which is 1.2 versus 1.2 volume percent, so it's pretty accurate. Okay, so you can do the same to calculate for UFL. So this 350, 4.76 times 6 plus 1.19, 14 plus 1, we get something like 7.57 volume percent, which if we compare to the data here is 7.5, so versus 7.5 volume percent, they are pretty similar.